Sound speeds. And once again, I'm going to apologize for the bad acoustics in this room. I recently moved and have not yet set up the acoustic treatment in the studio just yet. Therefore, I've also not set up the camera and lighting scenario in more of a permanent fashion. So you're going to have to deal with that as well. But that's okay. I'm not going to be talking about lighting, camera, or sound in this video, with exception of the way that sound is often delivered to us in the world of production audio this day and age, and that is not by cables. It is through RF. That's radio frequencies. So we're going to talk about the basics of RF and what you need to know. Now, keep in mind, this is a 101 type general overview, and it's not going to dive ultra deep. Believe me, we could go way deep down the rabbit hole, but we're not going to do that in this video, but we are going to kind of visualize a few things, and it's going to be kind of fun. So we're at virtual-graph-paper.com because I want to have graph paper to kind of help organize where we're going with this. These are basically squares indicating amplitude going vertically, and horizontally it's going to be RF. We have 0 megahertz, 500 megahertz, 1000, 1500, and 2000. Now, 2000 megahertz is also 2 gigahertz. So I'm going to be referring to megahertz in this video for simplicity's sake, and you'll realize why later. But if you notice, each one of these little stronger lines is basically a split in 100 megahertz. And then each one of them also splits down further into 4 parts, making it a total of 25 megahertz per little square. Now, this is going to help us visualize a few things. Now, this is very much outside of the legal spectrum if you go outside of from here basically to like here. So this is the only legal part. But we're going to, for simplicity's sake, we're going to pick a few frequencies. I'm going to go over a few things. Now, you say, why do I need so much room here? Well, let me explain to you. Let's start off with a red color here. We're going to put one transmitter out into the world, and we're going to set an amplitude. Let's just say there. Sure, might as well. And that's one transmitter that's on. Cool. Except that it's not really that simple, because if we were talking about sound and what we could audibly hear, if you have a frequency out there in the world, that is considered to be the fundamental vocal frequency, isn't it? And what is also out there in the world when you have a certain frequency? You also have harmonics and overtones. So there are the same exact things going on in the world of RF. So this is the fundamental, but I'm going to actually change, and let's do RGB. Let's do it in the order of cameras normally. So if you double 500, make it 500 times 2, you're going to have a harmonic that's, we're going to call it right around here. Okay. May not be exactly the right height in amplitude, but you know what? It's going to provide us with a visual here. The next one that we're going to have is the third order harmonic, or the next one that we would worry about is 500 times 3. So we're going to come up from 500 and we're going to call it, let's just say, I went down 3 before, we'll go 3 again. And again, this is not perfect in height. This is just giving us a visualization of the amplitude. Now, that is the fundamental frequency of 500 hertz. And then at 1 gigahertz or 1000 megahertz, we have our first harmonic and then our second harmonic. Now, let's go ahead and add in, just for the sake of it, a second frequency, because you don't normally use just one radio frequency whenever you're doing sound. So I'm going to put this one here. Let's go ahead and make this at, let's say, 550. Okay, so this is basically 500, this is 600, this is 550, so right in the middle. And let's go ahead and plug in those harmonics as well, so that way we at least have them. So twice 550 would be 1100. So here we go from here on up. And then we're going to add this one here. So again, going to go 5500 plus 1100 would basically be the same thing as 550 rather, times 3, which would basically take us to not 1500, but 1650. Is what that would be. If this is everything that RF did when you turn on a couple of transmitters, then we'd probably be okay, because the RF spectrum is, well, actually it's only from here. I think I said it was from here, but it's actually from just under here to just over here. That's the legal spectrum, is that little bitty bit, because the FCC has pushed us all the way down into that. It used to go all the way up to like here. lot of room. It was a lot of room to spread out. Now, granted, yes, we do have a little bit up through here right now, and there's a couple of guard band things. We're not going to get into that in this video, though. There's another video that I did on why you should get your FCC licensing. You should definitely check that out if you have any interest in RF and basically owning your own transmitters. But let's not get sidetracked here too much. Let's go ahead and dive into what else is happening. Now, first of all, because you have these two transmitters, one at 500 megahertz and one at 550 megahertz, the first thing you need to keep in mind is that there's intermod coming into play. Now, to explain intermod, I kind of need to explain spurious emissions, and that's basically anything that is a side effect, or rather a creation of having two fundamental frequencies interacting with each other. So it could create other frequencies that are basically additions or multiplications of them in very much the same kind of way that harmonics are. But there's other aspects of it too, and how frequencies will kind of come into play with each other. Keeping in mind that receivers can only lock onto one frequency at a time. And if these are basically transmitting one frequency, then it is all as well, as long as your receiver is only receiving one of those at a time. If you put two transmitters on the same frequency, your receiver wouldn't know what to grab hold of. It's kind of like when you drive your car and you have your radio tuned to one frequency, go from one big city to another, and in the middle, it's going to be picking up two different radio stations. Kind of the same kind of thing. They kind of fight and compete as your receiver tries to figure out what it needs to listen to. And that's one of the reasons why intermod comes into play, because transmitters have a lot of emissions that you need to be very aware of with regards to radio frequencies. So let's start plotting a couple of things here. We have 500 megahertz right here on this transmitter and 550 megahertz on this transmitter. Now, one of the things you have to keep in mind is that because there's 50 megahertz between the two of them, that's going to kind of be the width of some of the intermod. But there's formulas here you have to be aware of as well. So for example, the first one is we've already talked about, which would basically be 2 times the fundamental, which would be 1,000, and then 3 times, which would be 1,500. But then there's also a couple others that we need to be aware of. This 500 times 2 minus the other transmitter that's intermodding with it. So 500 times 2 is 1,000, and then subtract from that 5,500. And then it's going to create an intermod basically right here at about that approximate height. But then you have to do the same thing for the other transmitter too. So 550 times 2 is 1,100. Subtract from that 500, and now you end up with an intermod here at basically 600 megahertz. And if that's all there was, then we'd be in pretty good shape. But here's another thing to keep in mind also. There's also intermods that happen in each one of the harmonics. This is why this gets into being so much fun. And the intermod here is the equivalent of 500 and 550 added together. So it is actually about, let's say, I'll call it that height. And it is right between the other two. Notice it's still the same width, 50 megahertz. And it is directly right here in between those two harmonics, creating a little bit stronger than the two second order harmonics. It's actually creating a little bit stronger of a signal right there between the two of them, right there at 1,050. Oh, but we're not done just yet, because also over here, we have some even more modulation that's happening, because these two here interact with each other as well. And what I'm going to do now is let's just pick pink. That's going to be a fun color. And also, as you can imagine, it's going to be right over here and right over here. Now, the way you come up with that in the math is you would basically say this 500 times 3, or rather 500 times 2, and then add on top of that the 550. So 1,000 plus another 550. So 1,000 plus another 50. And then you do the same thing over here. You would actually take 550 times 2, making 1,100, and then add on top of that 500. So that's what comes up with this right here. So, or this one right here, rather, 1,600. So that right there is like, okay, there's a lot of RF happening in the air. Now, keep in mind that every single time one of these, little harmonics that start to happen over here, as it starts to deplenish, and over the course of the different harmonics going from 500 to 1,000, 1,000 to 1,500. Every time you have a harmonic or you have some of these spurious and other intermods, it's going to be lesser in intensity, not the same amplitude as the original. That would really suck if it was all extremely high like that. It's nowhere near the same amplitude in short, so keep that in mind. Now, we're also going to now, just for the sake of it, we're going to pull out yet another transmitter. And again, just for visual sake, I'm going to pick an illegal frequency. So we're going to choose 600 and let's do 625, which again is outside of the legal spectrum that you should not be transmitting in anymore. Okay, so let's say that we added another transmitter right there. Okay, now the first thing we need to do is say that's 625 megahertz. So if we were to create a harmonic for that, 625 times 2 is 1250. So we're going to go over here, and it's actually going to be right out here. So we're going to create that harmonic there. Okay, cool. Now we also need to do a third order. So we're going to do 625 times 3. That's going to be 1875. So 16, 17, 18, 75 right there is going to be where that one comes into play. Now, we've just done the harmonics. Now what we have to do is we have to look at this and say, okay, so between 500 and 625, that's a difference of about, 125. So we're going to start making some of these intermods. We're already on that one, so we're good. All right, so let's see. We would basically say, okay, 500 times 2 is 1,000. And now we're going to subtract from that 625. So we're going to go 1, 2, 3, 4, 5, 6, 25. There's one intermod right there. And now we're going to do the same exact thing on the other side of this. So we're going to say 625 times 2 gets us to there. Subtract from that 500. So 1, 2, 3, 4, 5. So now there's our intermod. And they're coming into play. Did I do that right? 500. Okay, so there, then there. Yeah, it looks right, I guess. But then we also have this other one here too. So 550 and 625. So that is basically going to be the equivalent of going here and then going over here. But then we also, okay, so you see how this is going to start to get very big very quickly because you're also going to have other intermods over here as they interchange with each other. Now, I'm going to totally get myself messed up here if I continue to try to do all this math. There's one in the middle there. There would be one in the middle there, and then there would be one in the middle between those two. Well, actually, I'm already starting to mess this thing up, aren't I? Hopefully I'm not. That looks like visually right in the middle of those two would be this one, right between those two would be this one, and right between those two would be that one. And then we would have to do the same thing down here. So those two intermods, holy cow, we're starting to get kind of, all right, let's see if we can figure this one out. Okay, between those two would be, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9. So that would be basically here. Correct me if I'm wrong. I think my math is going to be okay. And then between this one and this one is 3, 6, 9, 12, 15. So 15, that would be 5. So right here, down there, and then it would be another 5 over. I think that's right. I think so. But then what happens if we add a 4th transmitter in there? And then a 5th, and then a 6th? It gets cluttered up really quickly. Now keep in mind also, this is just the RF that we're putting out into the world. There's a lot of other RF that's starting to intermod from other sources as well that are coming into play with the transmitters that we put out there. This is an RF Explorer Pro Audio Edition. And if you're a pro that works in the world of RF and wireless and you don't have something like this, you might consider getting yourself one, at least for something like Tech Scouts. Now, this little bitty screen here is low res. It only can plot about 112 different points. And what it basically does is it takes whatever spectrum you're scanning for, like the entire 138 megahertz wide bandwidth that's legal in the United States, and it splits it into 112 different points and displays it that way. But if you connect it up to a laptop, it goes into what's called high res mode, where you can dial in on exactly what you want and see it and do additional scans, see high quality versions and lower and even higher resolution rather than what you can on this little bitty device. So we're going to do that just now and really look at the spectrum when you do something like turn on transmitters. And from my friend Scott over at RF Systems Consultants, I have borrowed 5 Zaxcom TRXLA3.5 transmitters. I'm going to be turning these on, and we're going to be looking at this spectrum on a high-res image on my laptop. Now I have my laptop on, and we're looking at the real-time scan of the air that we're looking at in the same resolution as that is on this screen right now. And on this RF Explorer, you can change most of the settings on the laptop with a couple of exceptions. And one of the big ones that we're going to be making sure that we turn on is under menu. You're going to scroll over to the right down to DSP, digital signal process. And we're going to make sure that's set to filter. The reason why, and then press return to get back. The reason why we're going to do that though is because DSP, when you turn that on, it kind of filters out through multiple different scans the average noise. I mean, it kind of scans in and says, okay, well, this is there, and then it's not, then it's there, then it's not. This must be noise, and it filters it out. Any other things that it detects routinely, it's going to say that's probably more actually not indicative of something that's there and not noise. So it's going to turn that on. Now, on your actual computer itself, notice that I have iteration set to 2, and I'm only doing that for our purposes here. Iterations basically is the number of scans it's going to display. There's a thin blue line that indicates what the most current scan is, and this kind of pinkish color behind that is more of the average. So if I turn off average, all you have is a little bitty faint blue line, but I want to actually see a little bit of what happens over the course of time. So right now we're going to look at this in a higher quality mode. So if I go over here to device, define sweep points, I'm going to turn it up to medium for right now. And all of a sudden you're going to notice it says, well, the display just went off, but you can maybe read that. It says high res mode right now. So I don't need to actually do anything more with this right now. We've turned the DSP to filter, but we're going to put that down to the side over here. And I'm going to start turning on a couple of transmitters. Now, this is the spectrum right now. And this is, notice the amplitude is in dBm. That's decibels in milliwatts. And I'm not using decibel watts, nor am I using microvolts, because this kind of gives us an even display of what things are in the air. Now, notice right now that my threshold is basically, we're showing and displaying all the way up to negative 100 dBm. Now, if you basically, whatever you set your noise floor for your RF coordination to be, it's going to take everything above that into consideration for your, when it's plotting out your frequencies. Now, we're not going to get into RF coordination in this video, but what I will tell you is that the higher it is, where your noise floor line basically is, and your white noise basically would be below that, and that's your threshold for wherever you set that line to be. If it's like set, for example, to negative 85, then anything above that is going to be used in your coordination, and that's not really very tight, because there's a lot of things that would be omitted if, for example, I take my bottom up to negative 85. We're barely seeing anything up there anymore. So it's going to be looking at all this saying, oh yeah, it's pretty good. There's no real anything that we need to be that concerned with. But as soon as you start to say, okay, actually, you know what, we're going to drop it all the way down to negative 100, and that's going to be where your white noise threshold is going to be. Any of this kind of stuff in here, which are basically television channels, by the way, television channels. I'm a little bit farther from Atlanta, so we're not getting them as high as it would be if I were in the city. But it's going to take into consideration any and all of this RF when trying to find the best places for our frequencies to be. So let's have some fun here. We have a spectrum set up, which is 400 to 700 megahertz, basically, which is outside of the legal spectrum. And we have a transmitter here we're going to turn on. This first transmitter, you're going to see that, you know, there's some television stations in here. I'm a little bit away from the city, so it's not going to come into play a whole lot here. But oh, look, there is our transmitter coming into play, which is at 565.1 megahertz. So that's right in line with where we're seeing it right here on the spectrum. So that is one transmitter. Now, if we want to jump ahead and see what that would look like, let's see, that's 565. What would double that be? That would be 1130, I think. So let's go ahead. And if we look at just 1125 to 1135, and we'll send that and look at it. We're going to also see that one of the harmonics is in place right here. It's going to be, did I do that math right? Yeah, there it is. Okay. I was going to say, I think it should be that. I'm going to turn this off for a second. You're going to see that harmonic die because if the transmitter's not there, it doesn't have that the ability to actually pick anything up there anymore because this is not creating a harmonic up there. Now, if I turn this back on, it's going to create that harmonic yet again. So I've just turned it back on. It takes a moment for it to scan because at this point, a sweep time scan of this wide a bandwidth is taking 10 seconds. So it's taking it a little while to actually come up there. And as soon as it comes through one more time and does a full scan, you're going to see that it's now got 2 iterations or 2 scans to create an average from. So its next scan, it comes back, it's going to give a full iteration and it's going to show it to you. What I am going to do though is put this over here to the side so that way it's not going to overmodulate with our receiving antenna. Now, what I'm going to do is I'm going to set this back to, let's go 400 up to 700. So it's outside of the legal spectrum. And I might also, just for our sake here, turn our device sweep points down to maybe high res. So it's not going to be as long to scan. Now, keep in mind also that each one of these horizontal lines or vertical lines of resolution, basically the vertical line that we see is, if you look over here, it is resolution bandwidth is set to 335 kilohertz. That means that it basically, well, actually, let's look at step first. 293.253 kilohertz. That means each one of these vertical lines of resolution represents 293.253 kilohertz, which is about a third of a megahertz. And in order to come up with the data that's displayed in that, it basically takes a look at a little bit a wider spectrum, which is the resolution bandwidth right there, 235 or 335. Geez, context, small screen, 335 kilohertz, which is slightly wider, and because there's going to be a little bit of a lead in, a roll off on each side, and it basically is going to consolidate the data in order to create this vertical point from that. So we have one transmitter up into play right now. Let's turn on the second transmitter and see what's going to happen there to the spectrum. Now, some of these television channels, we're going to probably see some modulation start to come into play here. Whoa, look at that. There is our second transmitter coming into play, which is at 512 horizontal, or 512 megahertz, which is right there, which makes perfect sense because it's right there between 500 and 550. But notice that the transmitter that's over here is creating modulations there and there, an intermod there and there. And now there's a little other spike that happens over there. Could be an intermod from any place. But let's go ahead and bring this over here. This overload compression right here is because these transmitters are so close to my receiving antenna on this RF Explorer. So it's like, whoa, it's so intense. But that's what all this is right here. And if I turn them off, you're going to notice that they go away. So I'm going to turn off both of these for a second. And the RF spectrum in the air is like, that's so much better. It's not nearly as much in the air. We're back to television channels. And my little area up here that I live in is going to be like, hey, look at that. It's so much more relaxed. But look at this. I'm turning on both of them again, and we're going to overload the air with RF. So we're turning them on, and as it scans, it's going to start to pick up on all these extra modulations from these transmitters. And it's going to hate me. Now, just because we can, we're going to also start adding in additional transmitters. Remember how every time you add a new transmitter, it starts to do even more calculations because it has to intermod and plan out all the different intermods between the other transmitters. So I'm going to add one more, just turned it on now. We're going to see where this one pops up on the screen. The very first one that pops up should be, we're going to see, where's that frequency? Up right there. What is this one? It is roughly around 239. And this frequency is listed as, or I said 239. It's 538.7. So close enough. So there we go. That transmitter is up, but notice it started to create even more intermods in there. So let's go ahead and turn on yet another one just for the sake of it, because it's going to be so much fun. We're going to turn on another one, and now you start to see all these other modulations start to come up, and look at this. It's starting to add a whole bunch of other little bitty harmonics in there. And all of these other things are starting to really come into effect. And just because we want to see the world burn, we're going to turn on yet another transmitter. We're going to really see what happens when we add another transmitter. And look at this spectrum now. This spectrum hates us. Now, this is the equivalent of having a couple of booms out and only 3 talent lavs. So 2 booms and 2 wireless. Now, you can see real quickly how it creates a lot of gunk in the air. And if I zoom in here, we can see all of these little spurs. all these little bitty things. And the waterfall down here is displaying a bunch of garbage in the air. So right here, if we want to just go back and unzoom everything and just look at the legal spectrum, let's say, let's go back to 470 and we're going to go back to 608 and we're going to look at just those in the legal spectrum. But first, I'm going to turn off all these transmitters yet again. 1, 2, 3, 4, and 5. All of these transmitters are now off. So if I send this, it's not going to pick up anything anymore. Look at that. Nice, hearty, good old 2.5 second long scan. And actually, you know what? Because we're going to do this in a smaller little area, I'm going to turn up. Actually, should we go super? Should we go ultra? You know what? Let's go to ultra just because we haven't seen it before. We're going to look at the most detailed scan that the RF Explorer can do. Now, this is the scan where there's nothing going on. This is a scan that's going to take roughly about 5 seconds to do. Actually, it looks like it's taking longer than that. What's going on? As soon as it finishes one iteration, it's going to tell me the scan length. Well, it's starting to populate in there. It should be telling me up there. But this right now at this particular resolution means that every single one of these vertical lines of resolution is only 33.699 kilohertz. So that's basically like slightly wider than 125 kilohertz step on some transmitters. So some of them are 35, some of them are 25. Either way. Now, because we want to watch the world burn, let's see what happens if we turn them all on at the exact same time and see what happens as these transmitters all go live. So we're going to put this over here. We have all 5 of these transmitters, which is basically the equivalent of having 2 booms out and 3 talent lavs. So 3 people talking and 2 booms. And this thing is scanning the air and it's hating everything it's seeing. And as it scans all the way through, which it says 13.5 seconds is what it's doing now. That's how long it takes to sweep the air. And it's going to start adding in more detail. Now, this would come into play a whole lot. We could really see it if we zoomed in here more. Like if I zoom in just in this area, we're able to see a lot more detail. Actually, this is taking so long. I'm going to go over here, sweep points, and we're going to turn this back into super. Let's not completely kill it. There we go. That's a much faster scan. Not nearly as high res, but you know what? We don't need to see it because it's only 138 megahertz wide of a span. So you can see all the RF that happens in the air. Now, keep in mind, frequency coordination isn't just saying, this area here looks like it's a pretty good area because there's not much going on there. And then there's another one. Let's just start throwing some transmitters in there. It's not that simple. Because there's also a lot of harmonics, there's a lot of basically intermods that happen all over the place in the spectrum. And you have to take all those in consideration. A lot of math that has to be done. And it's better to let a computer do that before you end up having to grab a pencil and paper or even manually do them yourself. Because a spectrum can go very quickly from looking very, very clean and good to having a lot of garbage in it really quickly by adding some transmitters. So I'm going to do one more thing here and turn on what's called the waterfall, which is a visual representation of what happens in the air. Now, currently, this waterfall, it should be pretty clear. Why? Okay, I don't need to save it, but there shouldn't be anything going on. It should be all like, pretty clear. But then why is it taking so long? I don't know why it's probably because of the, I've set it to, it's relatively slow right now. If I were to turn this over here to medium, let's say, it'll go a lot faster. So there's gray, which is default. This is pretty much blue is completely clear. And then anything that's gray is going to be a little bit of something that comes in to interfere. So if I turn on one transmitter, you're going to see it pop on in the waterfall as it happens. And as soon as it detects it in the scan, it looks like it's starting to pick it up right there. You can see the red. Now, if I turn on the second transmitter, you're going to start to see that pop up on the waterfall too, as it starts scanning up. So the second transmitter should be probably around here, I think it was. There it is. So that second transmitter pops in there, and then we add a third transmitter. And notice it's going to start to create more of this junk in the air by the time we add more transmitters. I still want to turn on this fourth one. Look at that one right there. So it's starting to pop up there. I'm going to turn on a fourth transmitter. Oh, look at this. Look at what's starting to happen here. These are starting to be some intermods coming into play. I just turned on another transmitter. That's number 6. Look at all this other junk that's starting to pop up here. Now let's add on number 7 just to watch the world burn. And we're going to see all of this intermod starting to come into play. So 7 transmitters should be coming on here. And look at all this now. All of this gunk and debris in the air, intermods that are starting to come into play. And all of that has to be considered in your RF RF calculations. So that's one of the reasons why we don't, as humans, really like to do that. We like to just leave that to a machine. Now, for our purposes in displaying something relatively quickly on video, I'm going to turn our resolution down to only medium, which is 512 points. That's going to at least give us a visual of what we're doing here. Now, if I turn on, once again, just to show you the way it works, if I turn on all of these frequencies, like here's coming on my boom, here comes on second boom, here comes on Talent Wireless 1, and here comes on Talent Wireless 2, and our third speaker that comes in just to say one line because the writer had to give him one line. Look at the way this all pops up here and all the garbage that is this in the spectrum. So this is terrible. All this junk that we're going to have to coordinate around. Now I'm going to kill all of these and we're going to look at one thing that you might have already forgotten about, but we're going to see. We're going to jump up and look at the second order harmonic area. So I'm going to scan the air, let's say at 1000 all the way up to, let's say, 1150. So I'm going to scan the air and we're starting to look in that area. Relatively clean up there, isn't it? Around 1000 to around 1150. Now I'm going to do the same thing. I'm going to turn them all on. 2 seconds later, 1, 2. There comes a second transmitter. 1, 2. Third transmitter. 1, 2. And last one. 1, 2. So now all these 5 transmitters are coming on, and look at the harmonics area. So much garbage, so much junk in the area. It was so peaceful looking there just a moment ago, but now it looks terrible, like complete garbage RF world. So I'm going to turn all of these off again, and we're going to go and look at the third order harmonic area, just because it's going to be so much fun. So I'm going to go up to now 1500, and I'm going to go to, what would that be? 1725, roughly, I guess, something like that. We'll see. Such a nice looking spectrum up there too, low noise and everything. Now I'm going to once again want to watch the world burn, and we're going to turn on all these transmitters and watch the RF spectrum up there go to complete garbage. So look at this. It's starting to pop up there, isn't it? Now keep in mind, that's just from 5 little bitty transmitters. The spectrum looks terrible. Look at how high this noise is. This noise is, actually, if I turn this on right here, we can see what the RF peak is. Negative 48, negative 43, negative 49, negative 45. So it's still up there pretty high. It's not by any means pretty. But remember, harmonics go up and they're supposed to drop off in amplitude the higher you go. So what we're going to do is one more iteration. We're going to, or not iteration, we're going to do one more scan. And we're going to look at it now from approximately 2000 up to, let's say, 2400. And let's look at what that area would be. So roughly up there. So there's a little bit of stuff going on up in there. This is mainly, we're getting into just below what you would have in the world of Wi-Fi and Bluetooth and that kind of thing. So it's still a relatively nice spectrum up there. We're going to turn all of our transmitters on yet again, and we're going to see everything that happens in that spectrum area. And it should be popping up here momentarily, and look at this. So we're messing up the spectrum even up there by using these Talent Wireless down here. Now keep in mind that with the harmonics and all the modulation that happens up there in those harmonics, it is happening, first of all, with a 4 times multiplier on it, because, and so that makes it wider, because while around the 500 and the legal spectrum, there may be a width like this. Every time you double, and go up, it makes the gaps wider for modulation. And it also means the amplitude's not going to be up nearly as high. So there is a lot of still amplitude issues going on here, but it's by no means as high as it was in the first order roll off area. So we're still seeing peaks of around negative 54, something like that. But still, it's nowhere near as bad as if we look at the legal spectrum, which is 470 to 608. We send that and booyah. Look at that area. That's complete garbage. So I'm going to turn the iterations up here to 16 so we can get a good solid average over 16 scans. And now our peaks of modulation are happening right in here. Negative 35, pretty bad. And just for the sake of it, just to see what it would look like in the highest possible resolution mode, I promise I can't talk. We'll look at it in the highest possible quality scan in the area. So we're going to put those down right now. That's a lot. And even if we zoom in here and look at any particular scan, let's look at around 510 to, actually, let's look at 530 to 550. Let's do that, because there was quite a few transmitters in that little bitty area. So we're looking at a very high resolution area of only 20 megahertz in 20 megahertz wide. And there's a lot of little spikes happening in there. There's a lot of modulation that's happening, intermod that's happening between all these different frequencies that we're transmitting in. Now, this is not very wide, and it's not as simple as just saying, oh, well, look at this right here, and it's pretty low right there, and it's pretty low right there. We're just going to throw them in there because there's intermods that take place in there too. The computer has to actually do all the math and scan, looking at the scan of the area and looking at these values, because every one of these little horizontal lines represented this area only 4.884 kilohertz. So it has to basically look at all of this, take the math into consideration over the course of multiple scans, and does DSP, noise removal process on it. And it basically says, I think that it's going to be best if we put transmitters here, 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 and here, because of the way they play. So it's not as simple as just picking a transmitter and saying, oh, you're going to go in this little gap perfectly. Because if you do, you could have conflicts from the intermod frequencies. So anyway, hopefully this gave you some insight into the world of RF. Thank you for tuning in this episode of Sound Speeds. Be sure to tune in the future for more overwhelmingly amazing knowledge of sound, RF perhaps, and of course, sound advice. Have a question you'd like answered or want to add something? Be sure to write it in the comment section down below. You can also make a suggestion for future topics of discussion. Again, comment section down below, or you can email me at soundspeeds@yahoo.com. Be sure to subscribe and turn on notifications so you won't miss out on future sound advice.